Welcome to the pre-recording of lecture 29 of MCS 572. So this is our second lecture on barriers for synchronized computations in the fourth part of the course. We started with high-level parallel computing and then went into message passing, parallel shared memory, computers, and GPU acceleration. So this is part 4 on pipelining and synchronized computations. I will not talk about GPU acceleration in this lecture, but I will consider the message passing to implement a parallel version of Jacobi method, an iterative method for solving linear systems. In the last part, I will indicate how to implement the Jacobi method in parallel using Julia in a multi-threaded implementation, so for parallel shared memory computers. Okay, what is the method of Jacobi? So we should imagine that we want to solve a linear system that is extremely large, so for many equations, many variables. We can reduce this to solving lower triangular and upper triangular matrices via the LU factorization, but in this lecture we do not consider a direct method. We consider an iterative method. So what this slide does, it considers a partitioning of the matrix A in a lower triangular, diagonal, and strictly upper triangular part. And then using the L, D, and U, we can rewrite the original equation, AX equals B, into a fixed point equation. And the fixed point formula that we derive at the bottom is well defined as long as every diagonal element is different from 0. So why is this fixed point formula interesting? Well, with the fixed point formula, we can immediately derive a fixed point method. Fixed point methods, as they are often used to solve nonlinear equations in numerical analysis. So you can verify in the rewriting of these formulas indeed that with the decomposition of A as the sum of a strictly lower triangular, a diagonal, and a strictly upper triangular part, that the original equation is equivalent to this fixed point equation. If you can solve the fixed point equation, then you can also solve the original equation. So the arrows are if and only if, and the situation is in some sense mathematically also very simple, in the sense that there is one unique solution. So that is what we assume here. There is one unique solution to the linear system, and all diagonal elements are different from 0. Okay, so we then have our fixed point method, a fixed point method which is very simple and attributed to Jacobi. So what is the virtue of this? You can see that the update formula involves the computation of the residuals, the b minus a times x. So in numerical analysis, we make the distinction between the backward error and the forward error. And here, what is so nice about this formulation is that the update, which will serve as an estimate for the forward error, or the error, if you like, that the update delta x also incorporates the backward error b minus a times x. So in numerical analysis, the backward error is how much should you modify the problem And here in this case, by how much should you modify the right-hand side so that your computed solution is the exact solution. So this is a conceptually very simple method, and in this course we need something that is very simple to define and that can give us a lot of work. So this method here is defined in the algorithm. So what we repeatedly do is that we repeatedly compute the update delta x by taking the residual b minus a times x and dividing every component of the residual by the diagonal element. So this is what the notation d to the power minus 1 means. So that's the inverse of the diagonal. So we stop when the forward error, the norm of the update vector, is less than some prescribed tolerance, here denoted by the epsilon. So this is a method that may not terminate unless we put a cap on the number of steps that we want to do. So we have the capital N, which is the last input parameter, and that is going to give a bound on the number of total iterations. So then there is the middle parameter, the x0. The x0 is our starting vector. For iterative methods to work very well, we better start somewhere close to the solution, but here we're going to ignore this. So we are just going to start with a vector that consists of all zeros. All right then, what do we know about the Jacobi method? Well, in some sense it looks like a very bad method, so a very simple method. But note that we have again a huge matrix, and the matrix is typically very structured. So note that what we actually do not really need is the big matrix, but we need something to do a matrix vector product. So it could very well be that the matrix is defined by a pattern. That for example, if we have a tridiagonal matrix, that we have formulas for evaluating the components of the matrix. So that actually that matrix doesn't need to be stored entirely, and also that the matrix vector multiplication can be done in linear time. But if we assume that this is a dense matrix, then the cost for one step is n square, and that is in the most dominant part, the matrix vector multiplication. So if the matrix is dense, if we don't assume anything on the matrix, and you can see with the theorem that is not a good thing to do, but if we have a dense matrix, and we will work with dense matrices, then the cost could be more than cubic. So the capital N could be more than n, more than the little n. So and then we have a cubic cost. But for these iterative methods to be viable and competitive to direct methods, we would need a linear cost or a lower cost to compute the matrix A times X. And also we would need already have somewhere a good enough starting vector so that actually we don't need that many iterations. Okay. We will ignore much of these things, but we will not ignore the theorem. So the theorem states that Jacobi method converges for diagonally dominant matrices. So we have the condition that the diagonal elements must all be different from 0. But actually, we need something much stronger. We need that every diagonal element needs to be larger in absolute value than the sum of all the off-diagonal elements. If we now look at rows or columns, I mean, it suffices that one is satisfied. So this condition, which we will not prove here, then also allows to generate good examples that will ultimately converge. But let us say why we are considering this in this course. It's an application of synchronized synchronized methods. So the natural, or one natural way, is to subdivide the matrix into strips. So if you work with 4 processors, then you can subdivide everything into 4 strips. So the strip partitioning is the first most likely and most logical one that you would be using. So if you have P processors, here 4 processors, then the 4 processors can compute the matrix vector product, or here the residual, then multiplied with the diagonal, can compute this completely independently from each other. So in some sense, this is already a pleasingly parallel computation, except that in every step we need synchronization. And also the norms essentially can be computed, so you should think about that the size of the matrix can be in the millions, but the number of processors, say, is relatively modest. So also the subparts of the norms can be computed in strips. However, you see the exit condition. So when we are going to use this in a parallel distributed memory computer, then every processor runs the same program, and every processor will need to know when to stop. So we'll use the needs to know the global information. So what that actually means is that it needs to do a synchronization. So here is the butterfly barrier applied to the one norm. So all norms are equivalent in linear algebra if you have convergence in the one norm. So the one norm is the sum of the absolute values. Then you also have convergence for the classical 2 norm, which is the classical or natural length of the vector. Okay, here you see the butterfly explained for 8 processors, or I'm sorry, for 4 processors. So in the previous lecture we've seen this for 8, but if you understand it for 4, you also understand it for any number. So if 2 people need to synchronize, it suffices that they connect to each other. Once 2 people are in pairs synchronized, then they can synchronize the other pair. So one of the first pair can contact one of the other pair, and vice versa. One of the second one of the first pair can contact the second person of the second pair. And this way, everybody is synchronized. Think about 2 couples going out for a date. Okay, so in this application here, we have that at the end, every processor. So this is a butterfly synchronization with something extra. So in the synchronization, every processor will send to the other processor the sum. So we'll send the portion of the norm. So this is a barrier, a butterfly barrier, which is also a reduction butterfly barrier. So at the end, and you can verify this, so when the 2 pairs are synchronized in the first step, you see that every pair has the 2 sum of the norms, and that gets sent then to the other to the others in the other pair. So you can verify that there is a receive and a send that's being done in the distributed memory setting, but this is also a reduction. So the effect after this barrier is that every processor will have the complete information of the norm of the update vector, and can thus decide whether to continue or not. Okay, so There is also the scattering that has to be done of the vector, of the solution vector. So the nice thing about butterfly barriers is that they work in a logarithmic number of steps, 2 log of the total number of processors. Now, sending one number is rather little. You may as well send also the entire portion. So what is here actually not explained on the previous slide is that you should not send only the norm, but you should also send the entire portion, the strip that was updated by that processor. So we have the communication overhead and the computation that is done. So in each step, every processor updates one portion of the vector, as much as bit of the dimension. And the total computational effort is thus n squared divided by p. So this is the summary of this algorithm. So let's now go through an implementation. So this will allow us to, perhaps I should scroll back. This allows us to introduce another very useful MPI command. That's the MPI all-gather. So the matrices that we use need to be diagonally dominant. Here is one way to construct diagonally dominant matrices with exact solution. So we start with a matrix of all ones, and we add to the diagonal the dimension to this. So then you can actually see that the sum of the off-diagonal elements is n minus 1, and the diagonal element is n plus 1. So we satisfy the condition that the matrix is diagonally dominant. The right-hand side is computed such that the exact solution is a vector of all ones. So this gives us a very nice test problem. Jacobi method is a slowly converging method, which also fits our purposes. We have something that takes a long time, but not too long, unfortunately. So it's a good test problem. So here are the parameters. We are happy if we find 4 decimal places in the answer. So we will stop the iterative method if the norm of the update is less than 10 to the power minus 4. The total number of iterations is proportional to the square of the dimension. So this is a very bad method. If you think of it, it takes cubic in the dimension. And we have a low accuracy. Never mind. Here is a run on an old computer, which I did not update. So on a 1000 by 1000 matrix, starting at the 0 vector, and you can see that it takes 8,000, more than 8,000 iterations in a sequential C program. And we get an error of 4.9 or 5.10 to the power minus 5 in less than a minute. Okay, so here is the C code, the main C function that has the parameters, the dimension, the matrix, the right-hand side, the tolerance, and the total number of iterations. What will be returned are the number of iterations used and then also the approximate solution. The strip partitioning makes that there are local variables. So inside the function, every worker, so this is a manager-worker paradigm, but still also the first processor will also compute the first strip. So every processor will allocate, the dx will allocate the y. So let us now look at the main loop. So every processor will compute the update. So we'll compute the portion of the update, and then we'll also compute the sum of the norms. So we are working with the one norm. So this is the sequential computation. I'm sorry. So this is still the sequential computation. So we have the update, the residual, essentially, and then we divide the residual by the diagonal elements. So this is a pure C code. How to make this run in parallel? So here is where MPI is helping us. So there is the construct gather to all. So we've seen the scattering of data from the root, from the processor 0 to all other nodes, and then also the gather, where every processor sends their result to the root node. But now the gather to all is that we have one result, so every processor has computed one number, and that gets gathered. It's also actually a scattering that gets distributed among all other processors. So here we have a vector of 4 elements. Every processor writes to that vector a specific number. So here the number is the identification number plus 1, and the at the end of the gather to all processors will have in the vector the same values as computed on all other processors. So this is the gather to all construct that is defined by the message passing interface. Here is the syntax, the MPI all gather. So we work with buffers. We don't need to give the source and the destination. So this is one other example of a collective communication. Every processor participates in this process. Every processor provides a buffer and provides a type and a count. And this is for all the processors that belong to the same communicator. All right, so here you see a simple run of the use all gather. So that's here the program. So the program fits on one slide. So one says that C is often low level, but one can define very useful programs, very short code as well. So you see the initialization of the data. So every processor has the same vector of p numbers. It's initialized to 0. So the ith processor stores the number I plus 1. So then we do the MPI all gather, where the all gather, the buffer is, the syntax looked very symmetrical, but here you see now there is at the source, so there is still a source if you consider this execution from the point of view of the ith processor. The ith processor will look at the ith data element, and it will be sent to the entire buffer. So this has the then desired outcome that at the very end every processor has the first p numbers. That's the example code. This has been implemented, so the C code is available on the course website. There is not that much that needs to be updated here. So there is the MPI all gather that is being done for the norm and for the x for the total vector, and you see that you get some very nice speed up on an unspecified computer. I believe it was the HP 800 with 12 cores. So the number of iterations here remained fixed. And you see that we have with 10 processors, we do have a very nice speed up on a matrix of size 1000. Okay, so the code now. So there is the running of the Jacobi method, where we provide so we have the strips. So we allocate the rows of the matrix. So dx and y are allocated for n rows still. We have the portion, and then there is the update. So the code essentially does not change much, except that now there is the start and the stop index. So the computation in should back up here. So you see that the critical parameters compute where to start and where to stop every strip. So in some sense there is not much reduction in the size of the matrix. So the sequential code has the modifications with the index and the computation of the portion. So the DMP computes the size of the strips, the n divided by p. We assume here that the dimension is a multiple of the number of processors. Okay, so we have the sum. So the thread or the processor with identification number ID writes its sum into the vector sum. So we have the update that's happening, and then we have the double MPI all gather. So we gather the components of the vector x, and then also we gather the norms. So we have a double gathering. And then there is the total sum. So every processor has in its MPI all gather has the sum and computes then the sum of all the components. And then you see the break. Okay, so that's basically it. We can compute without actually doing much runs, doing an analysis of the communication and the computation costs. So we have the total computation cost. We count the number of operations as 2n plus 3. And we also have the communication cost, which is depending on the size of the data, n over p. So we have the costs to send data over, which is proportional to the size of the data. And then there is also the startup costs. So this gets multiplied with p. So that's the total communication cost. And now we can predict certain scenarios. So here you see a completely synthetic evaluation, which kind of illustrates the computation cost, which goes down with the number of processors. So there is this hyperbola, that's the red curve. However, there is the communication cost that rises. So this is the blue curve. And you see that the black curve, that's actually the curve that we are interested in, is the total cost. And this illustrates that there is somehow a sweet spot for the number of processors. For the analysis that is done here for these fictitious numbers, the dimension, the t data, the t startup, we do have that the sweet spot is kind of around 12 to 13, 14 processors. So for that you have the minimal cost. After that, the overhead is going to dominate again. And then it certainly is not recommendable to use more processors. Here you can see the scalability. So what does this look now? You can make a multi-dimensional plot with this. So what's the difference between this plot and that plot? Well, here we have done it for n equals 1000. And then the next slide does it with n equals 10,000. You see that now, if you want to use 100 processors, you can. But then for this data, for the T data and for the T startup, your cost, your dimension must be 10 times higher. So instead of 1000 as a dimension, you must take 10,000. So this is a nice, rather dry but synthetic investigation of the scalability using the parameters T data, T startup. And this shows the scalability analysis, also confirming the laws of Gustafsson that we have covered in the beginning of the course, the first lecture actually. If you want to use a large number of processors, then you must pick problems that are also sufficiently large. Okay, so I have about 10 minutes left. I will say now something about the high-level implementations. So we covered MPI for pi. Here you see the all gather as available as provided by MPI for pi. So you have the all gather that is sitting in there. So I copied this from the Python documentation for MPI for pi, and this is a fairly self-contained piece of code which uses this gathering. So we are gathering with MPI doubles, so there is most likely also all gather with lowercase. The uppercase commands assume that you use structured data, that you work with arrays, so we work with NumPy matrices. So here what happens is that we do the all gathering of the number of elements in the vector x. So the matrix A is already available on all processors, but we're going to gather the portion of the x. So every vector, there's one, every processor here does one inner product and returns y. So I copied this from the MPI for pi documentation. Let's now do some other high-level parallel computation, but now with on a parallel shared memory computer using Julia. So using again the explanation for the Jacobi method, where we're going to apply strip partitioning to do the matrix vector products. And Julia has the package SyncBarriers, which provides a reduce barrier, which we will be using for the synchronization for the stop criterion. So this is a shared memory implementation. If we have updated X, then X is available at all for all threads. So the shared memory computation is in some sense a lot easier to do. So here you see a parallel matrix vector computation. So this is a code snippet. The matrix A and the vectors X and Y are not defined here. I will post the complete Julia program for this matrix vector multiplication on the course website. But here are the essential ingredients. So one can get the number of threads, specify the number of threads at the command line. The dimension of the matrices and the vectors is a multiple. So size is actually the size of the strip. So every thread in this parallel for loop, every thread, so the thread with thread identification number TDX, computes its start index and the end index of the partition. Keeping in mind that all arrays in Julia start at 1. So there is this offset of a 1. Then we can do the very simple slicing of the vector y. So the vector y is shared. But every thread writes in a different portion of the vector y. By indicating inbounds, this acroll inbounds is telling the compiler, we know what we're doing, do not check the bounds. So that's good for speed up. So just the strip partitioning here is defined with very limited amount of code. The second ingredient is the reduce barrier. So the reduce barrier is provided in the package SyncBarriers. This is a standalone implementation or demonstration where we're going to sum the first NT numbers. So NT is the number of threads, NB is the array or the vector with the first NT integers. So in the example you see with 4 threads, we are summing 1, 2, 3, 4. The reduce barrier, so just like with the butterfly barrier, when we compute the norm, we have to sum a vector of numbers, and we declare the reduce barrier. So what the reduce barrier will do, it will apply the operation plus to integer numbers, to NT integer numbers. So the sum S here is a global variable. So in the loop you have to indicate this with the global declaration. The reduce will essentially also make that every entry in NB will actually be filled with 10. So when you print out the sum here, you will actually see that the output is 10. So every thread will actually know that this is 10. So there is the reduction that is happening and also the synchronization. So you see Julia provides the parallel for loop, which we have covered before, and also provides the synchronization barriers. So these are the 2 ingredients that we need to implement the Jacobi method in parallel in a multi-threaded version. Here to indicate what is happening. So the entire program, I was thinking of dumping that on a slide, but it wouldn't really fit and it would be redundant compared to what we have covered before. So to summarize, every thread, so the ith thread will compute its strip of the update. It will update the strip. So the X no longer needs to be gathered like in the MPI implementation. In a shared memory computation, this is done. So after the computation of the norm, we have a vector, an array of P positive numbers, and then the reduce barrier has to compute this sum. And then every thread is going to check compare the sum with the tolerance, and then decide this as its stop criterion. Okay, a fairly simple recipe and effective. So here I've done 3 runs on Pascal. So in some sense, we've seen the multi-threaded implementation with BLAS. So if you really want a multi-threaded implementation, do not do it this way. Use the BLAS multi-threaded implementation of the matrix vector multiplication. Use that. So that's but then it's just one instruction and not really that helpful. So what we really wanted to explore is the synchronization. And you see here that going from 2 to 8 threads, the real time drops from 15 seconds to 5.4 seconds. There is a little bit the anomaly with the number of iterations. So the order of operations is actually a little bit shuffled. And you can kind of see that in some cases we actually need, with 4 threads, we actually need only 20 steps. So that's actually cutting the number of operations in half. So you can see that we have also somehow a super linear speed up. I actually am a little bit puzzled why that essentially happened. In any case, I hope this was interesting. So I was following the textbook of Wilkinson and Allen with the butterfly barrier to illustrate that the butterfly barrier can be used in the reductionistic sense, that you compute a sum of a vector that is then available to all processors. So we've seen also the MPI all gather. The main exercises is for you to experiment with this. So try also MPI for pi, try OpenMP. Another very interesting iterative method that can be defined with 2 simple formulas with a matrix vector product is the power method. So the power method computes the vector that corresponds to the largest eigenvalue of a matrix. It's actually, on paper, it's an extremely simple method. And it boils down to doing many matrix vector multiplications and also requires a synchronization. Very similar to what we have covered. The last exercise is going into the scalability issue. So can you actually, this is an optimization problem. So the total cost formula has had this minimum, so it went down very steeply, but then it went up again. Can you actually, and you can do the optimization, say, with SymPy or with the optimizers that are available also in Julia. With the analytic, with the parameters, you can actually compute the optimum. So this analysis model was quite simple. So next time we go into a better method, the method of Gauss-Seidel, and then I will also say something about applications. So in a way, there is parallel software available already. I should mention PETSI, and also applications to this, where, for example, the heat equation, where this is being used and applied. Okay, so this lecture serves somewhere as an intermediate between the idea of the butterfly barriers that was introduced in the last lecture and transitioning into more actual implementations and applications of these ideas.